Current. We'll start by defining electric current. Electric current is the rate of flow of electric charges, that is, charge carriers, through space. Specifically, it is defined as the amount of charge that flows past a specific location in a material per unit time. And here's our big equation. I stands for current, probably because C is already used for coulombs, and it's how much current, delta Q, over the time interval, delta T. The current will depend on the type of material that it's flowing through and the electric potential or voltage across it. Since we normally don't see current, the few times we do see it, it's not a very good thing. It's when you get a spark coming from an electrical outlet, or lightning, frankly, is electric current. So we want to have an analogy here to help us understand it. A good analogy would be thinking about water flow. The flow of water molecules is similar to the flow of electrons, the charge carriers in a wire. It's not exact, this is an analogy, and it doesn't always work, but it's a good way to get going. Water flow depends on the pressure exerted on the molecules of water, either by a pump or by a height difference. And by height difference, if you see water falling off a cliff, that's current. Electric current depends on pressure, in quotes here because it's an analogy, exerted by the electric potential difference, which is what we covered last unit. The greater the electric potential difference, the greater the electric current. The current, I, which is delta Q over delta T, has units of coulombs per second. Charge is in coulombs, time is in seconds, so we have coulombs per second. Coulombs per second can also be expressed as amperes, capital A. That is named after a famous French physicist, André-Marie Ampère, who worked in the early 1800s on electricity and magnetism. Very important person. Amperes are often called amps, and an amp is 1 coulomb per second. We know that if an electric potential difference is applied to a wire or a conductor, charges will flow from high to low potential, which is a current. However, due to a convention set by Benjamin Franklin, we express current in a wire now as the movement of positive charges, not the electrons which are really moving, and we call that conventional current. You can see if you go from high to low potential, you're leaving the positive end of a battery. That means those are positive charges moving. Now, Ben didn't do this to confuse future generations of engineers and students. It was already known that electrical phenomena came in two flavors, attractive and repulsive. Ben was the person who explained them as distinct positive and negative charges. So Ben arbitrarily assigned a positive charge to a glass rod that had been rubbed with silk. He could just as easily have called it negative. He had a 50-50 chance. Later on, the glass rod was found to have a shortage of electrons. They were transferred to the silk. So if the glass rod is grounded, electrons will flow from the ground to the rod. But the problem came in how electric potential was defined. Charge carriers will be driven from high to low potential, from positive to negative. For this to occur in the glass rod ground system, the conventional current will flow from the rod to the ground. And that's our definition. That's the movement of positive charges, opposite the direction of the movement of electrons. So it's backwards, but it's not a big thing. Just be careful when you're talking about current. The electrons will flow one way, but the conventional current is flowing the other way. Summarizing, conventional electric current is defined as the movement of positive charge. Even when in wires, what's physically happening are electrons are moving in the opposite direction. But if you have a particle accelerator, where the electrons are stripped off of an atom, making it a positive ion, which is then accelerated to strike a target. They do this in nuclear physics and particle physics all the time. The direction of the conventional current is the same as the direction for the positive ions. Here's our first electric circuit diagram. An electric circuit is an external path that charges can follow. Charges are moving along the electric circuit between two terminals using a conducting material such as copper or aluminum. For charge to flow, the path must be complete and unbroken. If you don't have a complete path, no circuit flows. No current flows in the circuit. For example, if this is a switch, and it's in that position here, the circuit is broken, no current will flow. This switch would have to be closed like that, and then you will get current. One more time on the definition, conventional current flow leaves the positive terminal and goes this way in a clockwise direction, when in reality what's happening are the electrons are moving counterclockwise. This is a pretty standard symbol for a light bulb. This is a symbol for a battery. The longer horizontal line is the positive end of the battery. A great example of a conductor is copper wire. And if we want to continue the water analogy, you can think of this wire as a pipe for water to move through. In other words, for the copper wire, electrons are moving through. If you have a water system, water is moving through the copper pipe. Example 1. What is the magnitude of the electric current passing through the heating coil of a hot plate if 36 coulombs of charge passes through it in 9 seconds? We list our givens here. We have delta Q is 36 coulombs, delta T is 9 seconds. We use our current formula, delta Q over delta T, 36 coulombs divided by 9 seconds, and we get 4 amps. Recall, please, an amp is a coulomb per second. A current of 0.60 amps flows through a resistor. How much electric charge would flow through it in 3 minutes? We start by listing our givens, 0.60 amps, and a delta T of 3 minutes, but we can't use minutes, we have to use seconds. So 60 seconds in a minute, that's 180 seconds. We have our formula for current, delta Q over delta T, but we need to solve for delta Q. So multiply both sides by delta T, and we come up with this equation over here. Then we substitute our values, current and time, multiply them, and we get 108 coulombs. How long would it take for 250 coulombs of electric charge to pass through an aluminum wire if the current through it is 0.50 amps? We start by listing our givens. Delta Q, 250 coulombs, current 0.50 amps. We have our current equation, but we need to solve for delta T. So we'll multiply both sides by delta T, and we get I delta T is delta Q. We then divide through by current. So now we have our expression for time. Now we put in the charge, put in the current, do the division, and get 500 seconds.